Thank you, Vinko. Good morning, everyone, or good afternoon, wherever you are. I'm Fausto Ferreira. I'm a leading researcher at the Faculty of Electrical Engineering and Computing, University of Zagreb. And I'm also part of the IEEE Oceanic Engineering Society. This event is supported by our student branch from IEEE OS here in Zagreb. And it's my pleasure to introduce Professor Hanumant Singh. He's a professor at Northeastern University. He finished his PhD in 1995 from the MIT Woods Hole Oceanographic Institute, and he worked there until 2016 when he joined Northeastern. His group has designed and built the Seabed AUV, the Jetyak ASV, and dozens of these are actually used currently in scientific and academic research. He also has strong interest in the development of unmanned aerial systems, normally called drones now. He has an extensive experience, you'll see by his talk. I'm sure it will be very interesting. He has been in over 60 expeditions around the world in support of marine geology, biology, archaeology, chemical oceanography, polar studies, and coral reef ecology. In collaboration with his students, he has won several awards, including ICRA Best Student Paper Award, Sung Fu Memorial Best, IEEE Transactions on Robotics Paper Award, and Best Paper Awards both at Oceans and AGU conferences. The talk from Professor Singh will focus on field robotics and on the current state, the past, and the future of field robotics. So it will show the evolution over the past 25 years in different areas, such as marine archaeology, geology, fisheries, and polar studies. Without further ado, I'd like to give the word to Professor Singh.
Oh, thank you, Fausto. So for that introduction, I sound really old. But anyway, so I thought I'd talk a little bit about some of the work that we're doing, and I like to start with this slide where on the top is, of course, the Titanic, and then we have the Seabed AUV. We have work we've done at a glacier and with drones. And many moons ago, even before I joined any of the labs, our lab in 1985 found the Titanic. And there's an interesting story here because what we do now is called field robotics. And field robotics now is, of course, one of the really growing hot fields. But again, this was before I was even a student. When they found the Titanic, the biggest conference for robotics is called ICRA, the International Conference on Robotics and Automation. And the committee there invited Bob Ballard, who had found the Titanic, to come and give a plenary talk. And Bob Ballard, said, okay, yes, I can give a talk, but instead of me, I'm a geologist. Why don't I send my chief engineer? And he sent Dr. Dana Yeager, who was my advisor and mentor in some ways. And Dana, the story is actually kind of interesting because he had submitted a paper to ICRA about the same work, about building this robot, and it had gotten rejected. And so then he went and he gave this plenary talk, and it was very well received. The whole, everybody loved it because he's a fantastic speaker. And of course, at the end of it, he said, here's what's wrong with our community. What's wrong with our community is we are so worried about control theory proofs that we don't appreciate real robots. And here are the reviews for my paper, which got rejected to this very conference where I'm now the plenary speaker. Okay, so that was kind of a funny story, but times have changed, and now, of course, this is an example of a paper that one of my students did, where he looked at SLAM, simultaneous localization and mapping, when we went back to the Titanic in the 90s, and that won Best Paper Award. And so it's nice to see that the community as a whole has progressed a lot. Okay, we have all these robots. We have Alvin. We have which is a manned submersible. We have Jason. They're getting used at all these interesting sites, including hydrothermal vents. We're doing sampling. We're doing all sorts of interesting things, right? And people are appreciating the fact that we're actually building real robots. Now, what I'm going to do is I'm going to focus on this one particular robot, which is called Seabed, which is on the bottom right, which is an AUV. But again, a lot of the stuff that I'm talking about is relevant to all these different fields. And the important thing now, of course, is that, since 2006, when DARPA ran these autonomous car challenges, field robots are now really appreciated for, bringing reality into the field of robotics. Okay. Now, the one other thing I do is I do imaging underwater. And with imaging, I'm just going to give you a little bit of background. Especially underwater, there are a number of issues that happen. If you look at most images, they're either green of underwater scenes, they're either green or blue. If they have true color, then they are, they have to be taken very, very close to the subject. Literally a few less than a meter away. If you try and take images from more than a few meters, then, because there's nonlinear attenuation of the electromagnetic spectrum, things look green or blue, or depending upon your camera. And then the other thing that happens is there are microscopic particles in the water column. And when you bring your own lights down, as soon as you start moving further away, you get this concept called backscatter. And what that is it's like driving in fog. If you're driving in fog, you don't want to put your high beams on because all the light gets reflected back by the fog particles, and the same thing happens underwater, and that's what you can see in the middle set of images, right? And then the other thing is, of course, we want to make large area mosaics, and the problem is, how do we actually take images and put them together? It's much harder when you're carrying your own lights down there. So these last set of images are overlapping, and they're, even though physically we can look at them, they're hard to kind of figure out where the overlap is. Okay, so one of the big things we've been doing, actually we did many moons ago, is we started understanding how imaging works underwater. And we look at cameras nowadays, and we've come a long ways. Originally, we used to always worry about how many pixels there are in the camera, how many megapixels there are in the camera. But underwater, what's more important is the dynamic range. How many bits of depth do you have? Is it a 12-bit camera instead of an 8-bit camera? And if you have 12 bits, what you can do is you can, we know that the reds have been removed because of the properties of seawater. We can amplify the reds without amplifying the noise. And so then we can get what are known as color-corrected images. And if we know a little bit about the scene, like maybe we can take that image and make it into what we call true color. It's as if we've taken, an image with sunlight, we've drained all the water from the oceans, we've taken an image, and then we put the water right back. Okay. So what I'm going to show you, for the most part, are images that have been corrected in this way, so that this is, and this is not normal even now, even though we did this, almost 20 years ago. It's still, we still find that there are people who don't do this. Okay. All right. So what happens? One of the big interesting issues that I'm very interested in is fisheries. Okay. And after you do all this beautiful color correction, suddenly you start seeing more fish. So in here right now, I'm sure you guys can all see this skate, even though it's kind of hidden. If I showed it to you in the original image, you wouldn't be able to see it because it's really hidden, right? But now what's really more interesting that one skate is there are actually two skates in this picture. So I'm going to give you a second to see if you can figure out the other skate. Okay, I wish I could see all of you because then I would make this much more interactive. But in any case, here's the second skate. You can see its eyes, you can kind of see its outline, its tail, and it's sitting right there. So this is one of the big problems underwater, right? Is especially when you look at fisheries, you don't want to undercount them, you don't want to overcount them, but right there, even in the images, fish are trying to disappear from you. And now here's a great example. Okay, this is a movie from Roger Hanumant, one of my collaborators. It's called Wow, it better be good. And so there you see, there's an octopus hiding right there. Now this octopus, once it realizes that we've seen it, it becomes really big. It tries to say, don't mess with me, I'm really, really big. We're gonna play this back in reverse just so that you see this. So there you have it. Okay, so there's that octopus. Now, one of the things I loved about this image is, I'm a computer scientist and as well as an engineer, and I was like, wow, that's a really interesting problem. How is that octopus managing to camouflage itself so well? Okay, and then you talk to the biologists, and they say the octopus is colorblind. Okay, so it doesn't even know about color, and it has this funky eye, and so it's a really challenging problem. And we're talking to students here today, and so one of the things I like to do in my life is find problems that are of interest to me that are very, very hard. Okay, and I look at this and I think of this as a really hard problem. How do we? And it's got two parts to it. One part is how do we camouflage ourselves, and the other part is how do we find objects that are camouflaged. And it's a problem that I can explain to you very easily, but I really didn't have an answer to it. And the reason I like these kind of problems is I'm working on all sorts of issues, and I want to have something in the background that's so hard that I keep talking about it, and it lets people look at it, collaborate with me, and maybe we can find an answer. So I thought of this as a very hard problem. I've given talks at MIT. People were very interested, and they were, and some of them are working on the synthesis problem. And then I found this other person from Los Alamos, and he came in. Lakshman Prasad is his name, and he said, "Oh, I'd love to work on this problem. Can I come to Woods Hole for a month?" And he came, and lo and behold, together we actually solved this problem. But before we solved this problem, and I tell you how we did it, let me show you some static examples. Okay, so here's the octopus right here. I don't know if you can see it. It's right in the center. You can see its two eyes, its arm, and it's camouflaged really well in this scene. Okay, and in this scene, here's the octopus. Okay, you can see its eye is really standing out, but if you watch my cursor, it's right there. And what's interesting about it is it's not, like the skate, it's not just putting sand on itself. It can only do certain things to its body and its shape. And somehow it's figured out what are the family of textures that exist here, and how can I blend to those textures. Now, I would love to have you guys think a little bit and see if you can find the octopus here. Again, I wish this was interactive because I would call on you, but I'm going to let you take 10 seconds and see if you can find the octopus right in here and in here, in these last two images. Okay, so I said 10 seconds, but in the interest of time, I might go a little faster. Okay, in this image right here, you can see that the octopus is right here. You can see its two eyes and its arm, and it's sitting right here in there. But I'm going to pick on Foster because I know he can turn his mic on and off. Foster, can you see the octopus in the last image?
I thought so. I didn't find it on the left one, but now I'm not sure. I thought it was this large thing on the top left corner, but
Top left corner.
no, it's here.
No.
Is it no, a bit to the right of that coral? There. Yeah. Is that the ice?
No, unfortunately not.
But
So I'll tell you.
Sorry, can I jump in?
There's no octopus in here. Okay, so this is the null case, and so that's also part of the interesting issue, right? And you look at these images and you say, "There's no way we can come up with an algorithm." And I'll cut to the chase. And with Lakshman Prasad, we actually worked on this, and we solved this problem. All those octopuses, we can find them, and in the image where there's no octopus, we don't find it. Okay, and here's what we did. Yeah, I'm using this other image as an example. You can see the octopus is in the middle, right there. Its arms are there, its eyes are there. We do, segmentation, and this is standard segmentation. It's a really good segmentation. It segments the whole image into lots of areas, and but it still doesn't find the octopus. I mean, it finds the octopus, but we have so many segmented areas, we don't know which one to look at. And then we do something where suddenly the octopus pops right out. And to try and show you what we did and set the stage, I also showed you all the false positives. And all the false positives are standing up mostly along the edges. And what we realized is that if you look at all these segmented images and you look at the perimeter, the smoothness of the perimeter gives away the octopus. And all biological organisms try to conserve heat, so they are usually very, very smooth compared to a rock or a coral reef, where they have different perspectives. And the reason we have all these false positives, which are very easy to filter out, is because they're on the edge. And when we compute the perimeter, the edge is very, very smooth, and that kind of biases our numbers. So it was kind of interesting, to think about this, and not just about this problem, which is an interesting problem, but the whole idea of trying to set up collaborations by picking on really, really hard problems and trying to make sure that you spread them wide and try and move the field forward. Okay, now I'm going to continue talking about fisheries for a little bit. When we first started out, we built these robots, and we said, everybody catches fish to count how many there are in the ocean, but by catching them, you kill them. And that's like trying to do a census of the human population by killing everybody on the planet and counting how many bodies there are. It's not a good way to go. Okay, and so can we just take pictures or otherwise, see the fish in their native habitat and then figure out how many there are? And so we have a robot. We can take very good images of the seafloor, and then we should be able to count how many images there are and do statistics to figure out how many fish there are in the ocean. Now, there's a problem with that. And the problem is fish are a little bit like people in front of a television camera, okay? There's three kinds of people. There's the people who see a television camera and they say, "Oh, television camera," and they come running towards the television camera, okay? And then there are people who say, "Oh, television camera," and they run away from it. "I don't want to be on TV," okay? Now, fish are like that. And if they come towards the robot, then what will happen is we'll see more of them, and we'll tend to overcount them, okay? And if they run away, we call that avoidance, and then we won't see as many, and so we'll tend to undercount them. And there's some fish who don't care, and those we might be able to get the right count. So there's this whole concept of fish avoidance, attraction, and it's a function of lots of things. What the noise is, whether it's acoustic noise, whether there's a pressure wave, where there's a light from a strobe. All these issues make a big difference, and so we've been trying to figure that out. And recently, literally now, well, actually, it's not that recently, 5 years ago, we did this experiment where we went and put small cameras on the seafloor, let the fish get habituated to them so that it didn't bother them. And then we ran our robots and, multiple robots, a towed vehicle, an AUV, an ROV, past these cameras. And we tried to see, because the time was the same in the robot and in the camera on the seafloor, we tried to see what the fish behavior was. So let me show you this movie. Okay, this is a movie from the underwater camera, and let's watch it. And you see the towed robot go by. And now the big question to ask is, were the fish affected by the towed robot? So I'm going to play it again. Okay, and so now you know what you're looking at. Now you need to tell me whether you think these fish were avoiding it or attracted to it or were not affected by it. And I look at this and I say, of course they were avoiding it. And then the fisheries people, they say, oh, don't look at the video, let's do the count. And their answer is, nope, there was no avoidance in this case. So it's kind of interesting. And these are the kinds of, and again, it's a function of species. Some species behave one way or the other, and we're slowly trying to understand this whole phenomenon. Now, the one other thing we did is, when we built this robot, the first time we built it, if you look at most AUVs, they are torpedo shaped. And we used to joke that the reason they are torpedo shaped is because the Navy paid for them. Okay, if the Navy pays for them, it likes torpedoes. And we got funding from the National Science Foundation to build one, and we built it. And we built it only for our own applications, archaeology, fisheries, and stuff like that. And then my student Oscar was had graduated. He was moving to Sydney. He wanted to look at coral reefs there. And so he said, I need to build another one there. Can I take the plans? And we said, why don't we just build you one? And we built another one. And then we started working with the fisheries folks at NOAA, which is our big fisheries agency in the US. And they liked it so much, they said, oh, why don't you build us one? And slowly we started building these, and eventually we started a little company. And now there are a bunch of them. They're all over the world. And that's also one really nice part about being an academic, is not only do you want to push the limits, but once you push the limits and do something good, you try and distribute it to everybody so that they can all do the same thing. And blankety blankety, the Australians and the NOAA folks and people in Taiwan, people in Puerto Rico, people elsewhere are now doing such a good job with these robots that they're doing better than we are, which is, I take that as a compliment. Okay, now I want to talk a little bit more now about working in the poles. Since 2007, I've probably spent like 15 or 20 expeditions going to the Arctic, the Antarctic, and Greenland. And it's been fascinating. And we again use the same kind of vehicles. Now, lots of people have been going to the poles. The big difference is the size of the vehicle. So this is two vehicles which are very famous, which have done amazingly good work. One is called, the one on the right is built by ISC in Canada. It's called Theseus. The one on the left is built by the British National Oceanography Center called AutoSub. And both these vehicles are, very, very expensive. So our idea was to actually go out with our regular Seabed, change its software, and do it for very cheaper. And now, there's a rule in robotics, and especially in field robotics. And the first rule in field robotics is that, we call it the first law of robotics, is that when you deploy a vehicle, the number of deployments should equal the number of recoveries. And, and if that doesn't happen, you're having a really bad day, okay? So here we were, going out, and what we would do is we would drop this vehicle, it would go down 4,000 meters. We'd basically make a hole in the ice. Drop the vehicle, it would go down 4,000 meters, it would do its mission. And in the Arctic, what's interesting is the ice is moving. So over the course of 18 hours, the icebreaker we were on would move like 10 kilometers away, okay? And what we would do then is come back with the ship towards where the vehicle was coming, find a hole or try and make a hole, and then try and guide the vehicle to the hole and recover it, And it's, and sometimes, like in the previous picture, things were beautiful. There was a big hole, the vehicle worked beautifully, and we could guide it straight into that hole and go and pick it up, okay? Other times, we couldn't make a hole. There was wind. We tried to make a hole with the icebreaker. The big pieces were all coming together. And even though we knew the vehicle was very close by, we couldn't see it. And if you can't see it, and if it comes up under the ice, you would tend to lose it, which would violate the first law of robotics. And so here's actually a nice picture. We knew the vehicle was right here. We were up in a helicopter trying to see if we could see it. No luck. Eventually, we brought it up, and I don't know if you can see my cursor, but we could see a little yellow thing just hidden right here. Okay, and we were lucky because if it had just been a little more bit there, we wouldn't have seen it, and we wouldn't have been able to recover it. And then, but again, was it worth it? And it was worth it because we found these amazing things about in the Arctic. One thing we found was that we found a volcano that nobody knew existed. Okay, in 1999, we were there in 2007, all the seismometers went off and people thought there was an earthquake there. And turns out it wasn't an earthquake, it was a volcanic eruption happening underwater. And so that was kind of fascinating. We also found these microbial mats. We went there looking for hydrothermal vents, but we didn't find them, but we found these microbial mats. And we actually managed to sample them. And when we sampled this yellow stuff, what we found were 13 new species that people had never seen before. And they were very high up on the tree. And so the biologists were really very, very excited about this work. And of course, when we did this, with lots of public outreach. We had a television crew on board. We had a website where we were posting every day. We would get answers. And that's all kind of fun, especially fun right now to talk about it because it's over. But when you were doing it there, it's sometimes it's a little less fun. There's a television camera person, and your vehicle has some problems, and you're worried about whether you're going to get it back, and you're stressed. And this person puts a camera, in your face and says, "Hanu, how do you feel that you might lose the vehicle?" And I think to myself, if I really told you how I felt, you would have to edit out of the movie anyway. Okay. And then all of us, we were there for 40 days. We had about, a little bit of time on satellite to call home. And, I would call home, and my 6-year-old daughter would say, "Dad, I heard you lost the vehicle again." I'm like, okay, great. Okay. So it's fun. It's a lot of work, but, but there are different parts to it. Okay, so now I want to show you a little video about after we went into the first trip, other people came to us and said, "Can you come out?" And here we're going out with the Australians. These are two of my students. Actually, one of them this is Clay Coons, who was my student then, and the other person is Peter Kimball, who was my postdoc. And both of them are now working at Google. Clay works on autonomous cars, and Peter works on actually on fisheries underwater at Google X. And in this case, we were actually not going very deep. We were going pretty shallow so that we could actually put a little GoPro on the vehicle so we get some imagery. Usually we're so deep that, it's hard to get a picture of our vehicle. And in this case, we were looking at sea ice. Sea ice both in the Arctic and in the Antarctic is melting really fast. So here we are in the Antarctic, looking at the underside of sea ice and trying to characterize what we can about it. And what was nice about this trip is that that little vehicle you saw, there was a little ROV, and we could take pictures from the GoPro because we were only, going to 35 meters of depth instead of 4,000 meters. And and here's the underside of the ship. This is the robot moving, and then we got this picture, which made the cover of multiple magazines just by luck. Antarctica is really quite beautiful, and working in conditions like this is a lot of fun. Okay, and what did we find? We found again. Stuff about the ocean and about sea ice that we just didn't know was happening. Okay, people thought the ice had a particular signature, and our signature that we came up with was way different. Okay, and of course this made all sorts of news. New York Times, BBC, you name it, they were all there. And some of them, it's kind of funny when you deal with the press. There was, I don't know how they got this. There was a picture with penguins in it, and there was a robot. And there was this one magazine which said, "Penguin-powered robot finds Antarctic ice is thicker than first thought." So you have to be a little careful about what happens, but it's still a lot of fun. Okay, I'm going to move on now and talk a little bit about this other vehicle, an autonomous surface vehicle called the Jetjack. And again, we built the first one. There's a lot of vehicles which exist, which are very similar to this one, and I'll show you a picture of it. And it's basically a kayak with an engine in it. And people have been doing that for a long time, and I want to do it too. The problem is electric engines are not as efficient as gasoline. And so, there was this company which existed, and they actually had a kayak which was designed with a small Subaru lawnmower engine. And once we saw that, I said, oh God, this is going to be really fast and it's going to last for a long time, much more longer than electric engines do. Why don't we make this into an autonomous vehicle? And the reason I wanted to do this is because, I have collaborators who are very interested in looking at the front of a glacier. They want to make measurements right in front of a glacier. Now, the problem is big pieces of ice are often falling off this glacier, so you don't want to be anywhere close to it. But if we could have a vehicle, which is relatively cheap, $5,000 for the vehicle without its sensors, then, hopefully you can get good measurements and it's autonomous. And even if a big piece of ice falls on it, it doesn't matter as much. And, and we could use it also in very shallow waters where AUVs can't go. And people are very interested in mapping those areas. And so we built this and we went out and used it. And I have a funny story, which is in this picture, okay? So when we were going out to this glacier, we would, the way it works is it's out in the middle of nowhere. You come into Greenland, and then you take, in this case, a 1-hour helicopter ride, and you camp with all your gear. And the helicopter pilot is really, your lifeline. He's your ambulance. He's brings you in and out, and he's also required, and he's worried about your safety, because if something happens to you, he will have to come out in maybe bad weather to come and pick you up. And the helicopter pilot was coming in with some new people, and he saw this picture of this Jetjack walking close to the glacier. And so he gets on the radio and he's shouting at us. He's like, oh, there's a kayak which is very close to the glacier. You need to come back. It's too close. You guys are going to get hurt. And we were like, no, that's autonomous. There's nobody there. And he was really angry. He was like, no, I can see it with my own eyes. Don't lie to me. It's right there. Bring that back, okay? And so, he came. He landed near a campsite, and he was a little angry. And we showed him this thing, and his face fell, and he was like, whoa, this is really autonomous. There's nothing in there. And so it was kind of neat to see that whole experience. And we got very, very good data out of this. And so, again, just like Seabed, once we built it, lots of people wanted to use it for lots of different things. And I think they're like, at last count, there are 25 of them all over the world working on different projects. Okay. Now, one of the other projects that I'm very excited about is, we could also use this for autonomous navigation. We all think about autonomous cars, but what I'm interested in is autonomous ships. And actually, in Norway, there's an autonomous ferry, which only does 5 minutes. It goes back and forth across the river, ferrying people, but it's completely autonomous. There's no pilot in it. And we're really worried about things like that. And there are certain rules that ship drivers follow. They're called call regs. And they, they say what happens when, a particular ship is going in a particular direction. How do they handle these issues? Okay. And so we wanted to see if we could, take our robot and make it handle these issues in very constrained environments. And so here's what you can see. Green is the Jetjack, and red is us in a small boat. And and we're trying to get in its way. And all the Jetjack has is a radar along with a map of the area. And this is a river. This is the Charles River in Boston, and which is very constrained. And so every time, and it's going under a bridge, every time we wanted, we would try and get in its way, and it would just always do the right thing. And, tell us, even when we were really being quite obnoxious to that boat, it did an extremely good job of actually following these rules. And of course, this is sped up. It's sped up about 40 times. It's not going as fast as this, but still, it was completely capable of doing this. And we're excited about this work. And right about, I think in this section, we got a little surprise. We did this in winter so that we had control. There was not very many boats on the river. But right about here, suddenly some boats showed up which were not ours, and they didn't even realize we were autonomous. And so, yeah, and so we hung around here waiting for those boats to clear, and it did a really, really good job even then. So I'm kind of excited. We have autonomous cars. We're going to have autonomous boats as well. Okay, and now the last thing I want to talk about is why we do all this. If you think about what's happening, my favorite story is, if you read about the polar explorers, in the First World War, 1908, Shackleton goes out, right? they would go out. Usually they were, British or Scandinavian, and the British were the funniest because they would go out. Shackleton goes out. He destroys his ship. Okay, before he does anything real, destroys his ship. They all are hurting. They get in a small boat. They, navigate the small boat to Elephant Island. And, just because they survived, they are heroes, right? They lose their toes to frostbite. They are all hurting. They come back to the UK and they are heroes. And all that would be fine, except for what do they do next? They turn around and go back and do it again. And there's a part of you that says, what's going on? These guys went, they didn't do much. They probably hurt themselves. And here they are. As soon as they come back, they want to go back again. Okay. And the first time I went to the Arctic, the same thing happened to me. Once you go there, you get what's known as polar fever. It's such a beautiful place. It calls you back all the time. Okay. And even nowadays, when we go, it's really one of the most beautiful places on the planet, both the Arctic and the Antarctic. And it's, rapidly diminishing. And, I wish we can, solve the problems associated with climate change so we can keep it for future generations. And and so I want to just show you, one small snippet of why, why this is such a cool little place. And so these are Adelie penguins, okay? And they're the most playful things. And now I'm not a cute kind of guy, but you look at this and you can't help but smile. They are the most curious things. They're like little kids on a playground, all playing, sledding on their stomachs. And it's kind of funny because in a second you'll see this ice floe before these Adelie penguins came on had on it an emperor penguin, and there it is. This, the bigger of the penguins saying, "Oh no, here come the kids on the playground." And so it's really a heartwarming kind of deal, and that's the kind of experiences you get in Antarctica. It's really beautiful. It's wonderful. There's lots of hard scientific questions that we need to figure out for the global good of society. Okay, and that's what helps drive my research. I'm going to end it right there. And of course, thank all my students, my postdocs, my collaborators, my sponsors. I'm just giving the talk. These guys do the work, and it's a lot of fun. And I'm going to end it there. And I would be happy to take any questions you might have.
Thank you. This was really interesting. I mean, I know most of the work you do, but every time there's something new to present and something to surprise us. So I'll open now the floor for questions. Please write in the chat the questions, and I'll say them to the speaker. Just give a couple of seconds for people to write them.
Hi, Fausto, can you hear me?
Yes. Okay. Yeah. If it works, you can also use the voice. Yes, please.
If it's not a problem, I just want to turn on my camera so that Hanu, you can see my background. And
I can. It's very good.
Yeah. Background is tightly related to the only equation you mentioned in your talk, where the number of deployments needs to equal number of recoveries. As a matter of fact, this equation was not fulfilled during one of the trials with Ivor vehicle that we had in our possession, and only 5 years after deployment did the equation become true.
Oh, that's fantastic, Nicholas, because I have to tell you, there's a second equation, okay? The second equation says that if you always follow the first equation, you aren't pushing the limits. So you are pushing the limits.
I wanted to say that, but it's not enough. Having that equation is not enough to be satisfied.
No. I mean,
you also need to recover a functional vehicle, so that's a constraint that needs to be integrated in the equation. But I love your talk. It was an excellent talk, really, really inspiring.
Thank you. No, we made up these equations in kind of as a kind of a joke, but there's a truth in them. You know, if you look at rockets, right? You know, the initial rockets, they would fire so many of them, and a lot of them failed. And even now, you know, some of them fail. And we don't have the kind of budgets that the people who do space do, right? And so, but our problems are just as hard. And so, yes, we like to follow the first law, but I tell all my sponsors this, like, look, we're going to lose a vehicle, and it's just a question of time. And I lost a vehicle. And so, you know, there is a second law. And if you're, you know, and if you lose a vehicle, even if you find it 5 years, that's pretty impressive. I think that must be the longest I've heard of.
It had nothing to do with our efforts, because after it was lost initially, we of course hired all the divers and all the boats around with all the sonars. Nothing was found. But 5 years later, on a Sunday morning, I received a phone call from a local guy asking me, did you happen to lose an underwater torpedo? And I'm waking up in the morning saying, are you kidding me? Who is this? And it was just a guy who randomly was diving in the area and happened to find the vehicle all of a sudden. So it's a strange story.
Very cool.
Hopefully, I will be able to tell you the details soon in person when this.
That would be awesome. I would love to hear that, because you actually, you know, you solved the docking problem for 5 years, which is amazing.
Never thought of it that way. I will acknowledge you when we publish this, right?
Thank you, Nicola. Hanno, we have a question from Roberto about what's your next projects and plans, because you would have stayed hours listening to more stories.
Oh God, what are my next plans? So, you know, next plans, more immediate plans, we're probably, you know, waiting for COVID to be over. You know, we have a bunch of cruises which got canceled or postponed. We're going to keep working with the fisheries people, Noah, Dr. Liz Clark, and then and we'll be going back to Greenland sometime soon as well. Mostly, what I didn't talk about because of time was the work I do with aerial vehicles with drones, and we're very interested in mapping icebergs and glaciers with drones. So we'll be pushing that in, hopefully this summer we'll be in Greenland, but again, it depends on COVID and how things go with that.
Sure, of course. I have a question myself, actually 2 questions. When you spoke in the beginning about segmentation and the octopus, I guess this was before the advent of deep learning and big data, etc., right? So it was much harder back then to have enough data to do good classification.
Sorry, Foster. I'm going to stop sharing my screen just because of I seem to have bad bandwidth. Could you repeat the question after? I'm going to just stop sharing this. And now, if you could tell me what your question was again.
About the segmentation of the octopus. This was before the advent of deep learning and big data, I assume. Right. So back then it was hard to have enough data. And I mean, I worked myself on that. I guess you're using template techniques, or how did you solve that problem?
So yeah, so that problem we solved just by using a bunch of computer vision problems. And now, you know, it's interesting because that's another area that I'm very interested in. We've been using these vehicles to collect lots of images, and we have literally, you know, 500,000 images sitting in our lab. Okay, and if I look at, you know, the Australian vehicle, which is called Sirius, that Stefan Williams and his group runs, they have more than 1 million images of coral reefs. But the big problem has always been is how to label that data for CNN.
Sure, annotation.
You know, yes, and you know, and usually, you know, if it's cats or dogs or cars, you can go to Mechanical Turk and you can pay someone 1 cent an image and they will label the image for you.
Yes.
But fish are very hard to do at the species level, and so just right now, I have a student who's been working on methods for labeling. And hopefully by the end of the year, we will release a data set with more than 40,000 images. I think there's 10 different species in it, lots of training examples, because we really want to push the limits in terms of doing, you know, automated identification of fish. And that's a big area. And I think a big issue is that we don't have label data. And so now we're going to put that in.
No, I agree.
Everybody to use and compare against. And so it should be fun. Yeah.
Yeah, I fully agree, and I think that would be a great contribution to the field to have that annotated data set.
Yeah.
And my last question was on the fisheries. So it was very interesting what you showed about having cameras and then go with the robots to see what happens with the fish, attract or avoid.
Yeah.
I know there's been plenty of work on marine mammal protection and monitoring to detect the impact of underwater noise and acoustic communications on mammals. But do you know if anyone is working on measuring levels of stress provoked by robots on fishes, and like if the avoidance of the fish was because of stress, or the attraction was on a fighting pattern or something like that?
Yeah, so it's usually, usually they would think of a robot either as a predator or something like that. So, they, what I was showing you was on Coral Reef, right? And on Coral Reef, there are lots of fish, so it's easy to see. But they're also used to seeing lots of predators come by. So I don't think they were being stressed per se. They were just acting normally. It's like, me driving down the road. If I see another car, I will make sure I don't hit it. I'll stay on my lane. But as you get into deeper waters, the amount of fish you see is much less. But then statistically, it makes a much bigger difference, and it's so much harder to quantify, right? So I think there's still some very interesting issues there. People have also done a lot of these tests in the lab. So for instance, when we look at light, one question is, when you're strobing a camera in the deep water, are you hurting the fish?
Yeah.
But turns out, no. They've looked at fish in aquarium where they keep strobing them for days on end, and nothing happens. There are certain wavelengths that they're very tuned to, but most of them they are completely unaffected by. Now, on the flip side, when a ship goes overhead, even though it's 100 meters underneath it, the pressure wave from the ship, they often feel that.
Yeah.
And then Larry Mayer has this beautiful, people use acoustics from ships, and Larry Mayer has this of fish of school coming straight to a ship and going around it, and and so not being counted at all. So there's all sorts of interesting issues, not just with robots, with acoustics, just like you said, with marine mammals. We might be actually, interfering with their basic abilities. Here, it's just like interacting with the environment. So I don't think it's as bad as that.
Yeah. Sure. We have one more question from the audience. So actually two. One is, if you consider designing some sort of bioinspired robots, something like fish-like or turtle-like, that would not disturb the fish while counting them.
So that's a great question. There are people who have actually designed a bioinspired robot, and the problem is, it's that the fish aren't just disturbed by robots; they're also disturbed by other fish. So if they see a strange-looking fish which is bigger than them, they might think, okay, this fish is coming to eat me, and run away from it anyway. So it's not a function of whether it looks like a fish or or looks like what we think of as a robot. It's a function of what are the fish you're trying to study. Okay, so so it's the shape almost doesn't matter, unfortunately. Camouflage is only good for if you don't want to get eaten, right? And so so camouflaging a robot unfortunately doesn't make that much sense. Now, from a bioinspiration standpoint, it might make sense to have a flapping foil. Some people will say that in the long term, it's more efficient than a propeller, and that might be true. So there are certain parts of bioinspiration that we can take into the design of our robots, but making it look like a fish, maybe not.
I see. And yeah, the other question is, given your interest in multi-domain scenarios, if you're looking also at cooperative missions with the AUVs, ASVs, and aerial vehicles.
Yes, of course. All of us are. And I think that the big problem is, it's hard to get, two vehicles to work at the same time for long periods of time. It's much harder to get 4 or 5 of them to work. I have a program where the program manager said, my goal is to make sure that you can fly 8 drones at the same time, but not only are they flying, they are communicating with each other, they're doing images, and we can talk to all of them, and we can program each one of them, and that's a big challenge in itself. So yes, it's a hard problem, and but it's an interesting problem, and we're all excited about it.
Thank you. if there are no further questions, we have a few minutes. So if anyone has any more questions, please feel free to put them now before we close the call. If not, yeah, I have if there's no more questions, I'll have one last question regarding polar robotics, which is, what's the hardest thing that can happen or to do in polar, like when you have a deployment in Antarctica or the Arctic? What's the hardest for you as a scientist? Of course, it's hard to be away from family sometimes, even it's during Christmas because it's the summer there. I know people that go and do Christmas in Antarctica, but in terms of science and mostly in terms of polar robotics and deployment, what's the hardest part in polar robotics?
So, in polar robotics, the hardest part is it is such a risky environment to work with that people are almost afraid of losing their vehicle. And, if I look at some of the other vehicles, they cost so much money that they really are worried about the first law of field robotics. If your vehicle costs $15 million, you don't want to lose it. Even if our vehicles, which cost $750,000, an order of magnitude less, we don't want to lose them, but we're a little more, risk-taking. And there's some very hard problems that we want to solve. So, I didn't talk about it, but one of the other interesting problems is all the measurements we take is in austral summer, when it's summer, when it's easier to work there. But we don't have enough measurements in the austral winter. So a couple of years ago, we went on this expedition where we went in autumn. We went in there, where springtime was, where wintertime was coming, because they wanted to make measurements there. And every time we go out to the Arctic or the Antarctic, our icebreaker often gets stuck. It gets stuck in the ice. And, when it gets stuck in the ice, we usually know that hopefully we can break out. And if not, we just wait. And a few days later, the ice will shift and we will be able to get out. Okay. Now, if you go and you get stuck in the autumn, then you're going to be there for a very long time. You don't want to be there overwintering. But those are the kinds of measurements. People stay in Antarctic field stations over the winter, but they don't, venture out. They can work at the station, but not very far from it. And so those kinds of measurements are really what are required, and we're slowly working towards them, which is kind of fun.
Thank you. Thanks again to you, to IEEE Region 8 Young Professionals for helping organizing, and to all the participants. It was a great pleasure to see your talk and to get your feedback on the questions. And I hope to see you soon, hopefully next year in the Oceans Conference or some other opportunity when we are able to travel again.
Absolutely, it would be wonderful. And to everybody who is here at this meeting, the one other thing I would say is, if you're at a conference and you see me, please come up, say hello. And not just me, anybody in the field, because as a field, we love having young people join our field and become, start contributing. And you guys are the famous, are the future stars that we look forward to interacting with. So take care, guys. Thank you so much for inviting me. And hopefully we'll see each other in person one of these months.
Yeah.
Okay.
Thank
Bye-bye.
you. And for whoever who doesn't know our society, you can Google IEEE Oceanography Society and know more about what we all do in our daily jobs. Right. Thanks again, and bye to everyone.
Thanks, bye. Thanks, Kano.
Bye.
Bye.
Bye, Nicola.
Bye.
Bye.